Hi, today we will talk about signal integrity, which is a continuation of the previous lecture on ground planes, where we had these ground planes acting as a reference plane for the tracks above or below them. And we said that especially for high frequency signals on these lines, on these tracks, we have to know the impedance of the tracks, and this impedance should be well controlled. So why is that so? And the answer is signal integrity. So what is the signal integrity anyway? The signal integrity deals with transmission lines on printed circuit boards and how the properties of these transmission lines affect the signals. And what are these effects? Well, you can have distortion of the shape of the signal. Of course, we have some delays as well because there is a finite speed of that signals. We have some reflections on these transmission lines, and therefore we have to terminate them properly, which is a solution to minimize the reflections. And we also have crosstalks between the lines. All that is covered in this signal integrity, which actually is a whole separate field of studies. We will just tackle it a little bit. First of all the signal integrity talks about how the electromagnetic field propagates through so-called transmission lines. So what is EM field? What is the EM field we're talking about? And what are the transmission lines? Well, electromagnetic waves, we all know, it's a hand-in-hand propagation of electric and magnetic field through empty space. And what we determine here is the wavelength, the frequency, and so on and so on. So we will talk about transverse electromagnetic field, or TEM, where E and H vectors are perpendicular to each other and also perpendicular to the propagation speed. We all know that this electromagnetic field propagates in vacuum with the speed of light, which is 3 × 10⁸ meters per second. And you should also know well how the wavelength and frequency are related. What else? The next important thing you should know about electromagnetic field is so-called wave impedance, which is a ratio between the amplitudes of electric and magnetic field components. And for TM wave, we can define it as a medium property value. So this value is only dependent on the medium through which that electromagnetic wave travels, and it includes also the conductance of the medium. And this is a frequency dependent value. But if we have an ideal medium without any losses, so that conductance goes to 0, we have infinite resistance, so totally non-conductive material, then the wave impedance becomes very simply permeability over permittivity, and it's a real value and it's independent on frequency. And this is what you should remember. What else? The wave impedance of this electromagnetic space in electromagnetic field in empty space is simply just the basic constants ratio, which would give you around 377 ohms. And that's another value you should remember. And the speed is the speed of light. But if you put it in a homogeneous dielectric where the relative permeability is 1, then you get the value of Z0, which is this one, divided by square root of epsilon relative. So this is another value you should remember. And finally, the speed of that wave is just simply 1 over mi epsilon square root, and which gives you this relation. And finally, if you are in a homogeneous non-magnetic material, this is the final equation. The speed of the propagation is just the speed of light over square root of epsilon r. Again, this is equation you should remember. So that one, and these two. So we know now the basic properties of electromagnetic field propagating through empty space and through some homogeneous dielectric. What are the transmission lines then? Well, transmission lines can be of several shapes. You can have coaxial line, you can have two-wire line, you could have just parallel plate line like here. And on PCBs we usually have so-called strip lines, microstrip lines, and other forms such as coplanar waveguides. All these transmission lines are actually transmitting transverse electromagnetic field. But there are also others which do not transmit this order of field, but also higher orders. So these are the ones we will be talking about on the PCBs. Strip lines, microstrip lines, and coplanar waveguides. So if we have a transmission line, actually we can replace the electric and magnetic field with the voltage and current. So now the voltage is traveling along the lines and the current as well. The current is also, the electrons are traveling back and forth and therefore generating magnetic field, and voltage traveling along the lines is generating electric field. So we can also say something about the characteristic impedance of transmission line as well, and which would be just a simple ratio of two amplitudes of voltage and current at a certain position. And electrical transmission lines then can be modeled as a small lumped component circuits. What are the lump components? These are these resistors, inductors, conductors, and capacitors expressed per unit length, which is called lumped elements. So we have ohms per centimeter, nanohenries per centimeter, and so on and so on. So we have a series impedance, this is that one, Z series, and we have a parallel admittance. And all that together forms so-called parallel admittance, and all together forms characteristic impedance of the transmission line. So we can build up this transmission lines by taking a lot of these short pieces represented by this circuit, and we can build up the whole length of transmission line. So the characteristic impedance, as you see now, is also wavelength dependent. But if we have ideal transmission line, that resistor would go to zero and that conductor also. So that means that we have ideal copper lines and we have no current flowing between the line and the ground, so ideal dielectric. And then this transmission line would change into that one. So we have ideal lossless transmission line of some certain length, and each this section represents a small dx of that length. And that dx should be shorter than, let's say, wavelength of the signal over 20, which actually represents the maximum wavelength of the signal that is present on that transmission line. So if we have enough of these sections forming the transition line, we can simulate it very, very thoroughly. Now, the characteristic impedance of the lossless line, where the resistance and conductance goes to zero, is simply this equation here. And it's a real and frequency dependent equation. This is what you should remember. The signal propagation speed then forms this equation here, and this is another equation to remember. And finally, the propagation delay is just the time needed for this signal to travel along the length L. So that's the third equation. So higher the speed, shorter the propagation time. Okay, and for the two most typical transmission lines on the PCBs, which is a microstrip and strip line, we have some empirical equations shown here. And all the others also can be expressed with these empirical equations, of course a little bit different ones, but each form of transmission line can be calculated its properties according to their dimensions. So you see here that the basic characteristic impedance of these two transmission lines contain its physical dimensions and the properties of the dielectric here and here as well. So that means that what you should be careful about in order to construct such a transmission line is just following and calculating all the thicknesses according to the wanted transmission line impedance, and then make it according to these results. And from that on, you can also calculate the propagation speed and the propagation delay, of course, out of it, the capacitance per unit length. This is the capacitance per unit length, and also from that, and knowing the impedance, you can calculate the inductance per unit length, because the impedance is just square root of L over C. So you can calculate the other one out of the known impedance. So I told you before that the propagation delay and the speed actually of the signal of the electromagnetic wave in a homogeneous medium would be just the speed of light over the square root of epsilon relative. So here it's quite obvious, but here it's not. Why? Because there is some field present also in the air. And here is the epsilon relative. So there is a part of field in the air and the other part in the material. And that affects the speed. More the electric field is in the air, the higher the speed. More electric field is in the material with the higher permittivity, the lower the speed. And if all electromagnetic field would be inside the material, you would get this one there. Okay, so the fastest transmission lines are also the narrowest ones, and those who are further away from the ground plane. But there are many uncertainties you should be aware when calculating this impedance and other properties of transmission lines, such as permittivity values, which are only which can be of the dielectric or the solder mask on top. All the permittivity values are these are the epsilon values, are affecting the impedance, of course, and they are dependent on the frequency, on the moisture content, on the material itself, from the batch to batch, it could be different, and so on and so on. There are many, many influences to these relative permittivity values. The tolerances of track widths, all the mechanical tolerances as well. And the solution is that the manufacturer actually build some test structures on the PCBs and measure the actual impedances, and then they tell you, okay, in our process, this design, this layer stack has to have this width of the tracks to achieve a certain impedance. And then you can take these dimensions from the manufacturers, and then you can construct your lines according to their rules. And then they assure you to have impedance uncertainties between, let's say, 5 and 10%. That's quite a lot, but it's quite hard to achieve on the other side. So we have different calculators we can use for typical transmission lines, single-ended or differential ones, using so-called Saturn PCB calculator. And in that calculator, you can enter different values, different properties of your designs, and then you would get all the parameters for the transmission lines out of it. So it's quite useful. And I used it to calculate different typical widths of the most used transmission lines. Here are the microstrip, here is the strip line, and here are the coplanar lines, coplanar waveguides. All that values here can be taken and used. And maybe I can just point it out that on a very thick substrate, like classical 1.5 millimeter thick substrates, you would have troubles reaching, let's say, 50 ohm impedances, because you would need very, very wide tracks. So that's one of the reasons why double layer, two-layer boards are not suitable for reaching low impedance tracks. Well, you can use more layer boards, let's say 4 layers at least, and then choose the one which has very, very low, short distance between the dielectric, between the top track and the first ground plane through the dielectric, let's say that one or that one. These two then will give you very easy controlled impedances with narrow tracks for reaching different values. So all that should be taken into account. For example, if you want to use a 50 ohm track on a 1.5 millimeter, it's better to use coplanar line than normal microstrip line, because in the coplanar waveguide actually you would get the same impedance just by 1.2 millimeter wide track, which is still very wide, but it's narrower than here, 2.8. Okay, what about the signals propagation now on these transmission lines? Now we know what are the properties of transmission lines. We know that we have to care about electromagnetic field. But now, what are the how does these properties of the transmission lines and the electromagnetic field actually affect the travel of the signal. This is an example of a transmission line. So that's the transmission line. And this is the generator, which has some source impedance, and there is some load on the other side with the load impedance. And we mark the beginning of the transmission line with letter A and the end with the letter B. So we have voltage A at the beginning and the voltage B on the end. And the transmission line has a characteristic impedance of Z0. And we have a pulse generator, which generates very short pulse and sends it over the transmission line. And this is an example where we have the same impedances. So the source impedance is equal to the load and it's equal to the characteristic impedance. So everything is well matched. Let's say we have a 50 ohm line. So we have a 50 ohm line, 50 ohms, 50 ohms. And now I will show you what happens. So the pulse travels along the line and it gets dissipated on the other side. That's it. As simple as that. That's ideal signal transmission. The only thing that actually still affects the signal is the time delay. So the only thing that is here is a time delay and nothing else. Everything else is perfect. We have an ideal signal shape, it travels along the line, it gets absorbed on the other side and nothing else happens. So now let me analyze a little bit that traveling of that signal a little bit further. The first question you should ask yourself is, what is the amplitude of the signal on the line? Well, that's what we have to look at the generator side. So we have the generator here. It has a source impedance, generator impedance, and it's connected to the transmission line. The transmission line acts as a load to that generator, but you should ask yourself, what about that one here? And the answer is, the load impedance on the other side of the transmission line doesn't have any effect on the initial signal at time zero. When at time zero the pulse generates, it doesn't feel what is on the other side. It doesn't feel it because it didn't reach it yet. So the end of the line is like an unknown thing. It's like a pitfall for the signal. You don't know what is there. So the signal generator, let's say, feels only the impedance of the transmission line, which means that the voltage which builds here, we call it initial voltage. Initial voltage, UY. This voltage is calculated as a voltage divider between the generator's source impedance and the impedance, characteristic impedance of the transmission line, which in our case, which we have Z0 50 ohms and the generator Z at also 50 ohms, that means that the initial voltage is 1/2 of the generator voltage. So this gives a little bit of needs or requires a little bit of deeper thinking, because now what we have on our transmission line is just half of the generator voltage. Is that acceptable? Well, depends. It is acceptable if we have analog signals we want to transfer to, let's say, antenna. But if we have digital signals, we want to reach logic levels. And if we have, let's say, 3.3 volt system, and we put 3.3 volts on the transmission line, and only half of that is traveling along the line, that's a problem, isn't it? Well, it may be or maybe not. Depends what is on the other side. But let's say we want to achieve logic level already at time zero. If we want to achieve logic level just at the time, already at the time zero, we have to have very low impedance of the source, much lower than the impedance of the transmission line. And this is the criterion here. If we want to achieve logic level, logic 1, already at the initial time 0, then we need very good generator. And if we take a typical microstrip transmission line on FR4, we get to around 125 ohm characteristic impedance, which would require very low resistance of the source, because if we want to achieve 90%, let's say 90% of the maximum voltage already at the beginning. So these line drivers that are using it, that are used in the digital systems to drive the transmission lines, have typically, that's why they have typically these output source resistances. And there is another graph now which I would like to pay attention to you. That one on that left hand side is very simple. It just shows you the generator resistance or impedance, whatever, and the initial voltage. And of course, that holds for the 50 ohm transmission lines. Now, that means that if you take, for example, ideal generator, you would get maximum voltage. If you take 50 ohm generator, you would get half the voltage, and anywhere in between. So using that, and you also knowing what are the properties of different logic families, and these are, let's say, just part of the logic families of the digital systems, you can quickly see that there is some minimum impedance of the line that would still allow logic 1 to be transmitted directly at the beginning, at the time 0. And that is dependent on two things: the generator resistances or impedances, and what is the logic high level with respect, how it is determined with respect to the, let's say, I would say, the power supply voltage, or VDD, let's say. So how much is the high voltage level? And these two values are known for these different logic families, and they are determining the minimum impedance of transmission lines which can be used with these logic families. All right. So what else? Well, not only driving, that's just the first initial part of the transmission of the signal on the line. The next part, of course, when we get the initial voltage, this initial voltage then travels along the line and hits the load. So what happens then? We want to know what happens on the load side, and usually we get some sort of reflection. So what is a reflection? Well, a reflection means that a part of that signal gets absorbed in the load and the other part gets reflected back. So why does that happen? The thing is that impedances play a major role here. The voltage and the current, let's say this is the current and this is the voltage on a certain point of the line. The ratio between the voltage and current is the impedance. Now I come to this point when my transmission line ends, and what happens on the other side is that the ratio between the voltage and current is now the load impedance. And if that one is different, we have a discontinuity. A part of the current has to flow back, or part of the voltage has to be reflected back, so that these two equations would still hold. And this is called reflection. So we have an incoming wave here, we have a reflection, and we have the transmission. And the reflection is determined by the so-called reflection coefficient gamma. And the reflection coefficient is calculated with this equation: Z load minus Z0 divided by Z load plus Z0. So this is the one you should remember. How would you remember that equation? Well, the easiest way is to remember it through the most typical, or let's say special cases. Special case first special case would be that you have Z0 as a termination resistor. Then your reflection coefficient of the in point B, so that side, is 0, as you see. But maybe we can put a short circuit. If we put a short circuit, the Z load would be 0. Okay, we put 0 in, we get -1, minus over 1. Okay, -1 is the reflection coefficient if we have a short circuit. If we have an open circuit, then the impedance of the load is infinite, and that would mean infinite over infinite is 1. We have reflection coefficient of 1. So these are 3 special cases, limit cases, which can help you to remember this equation, which is quite easy for, you know that you have a sum of 2 impedances here, and here you have a difference. So which one is on the first place? Well, if we want the gamma to be 1 when you have open circuit, the infinite part should be in the first place, right? Okay, and that's then way to remember it. Okay, let me show you now a few examples. First, I will show you that one, which has the same impedance. So the source impedance, the generator impedance, is the same as the characteristic, and the load impedance is larger. Here you can see we have 50 ohms, 50, so it's the same, and here is 100. So here the gamma on point A is 0. Here gamma in point B is 100 minus 50 divided by 150. So 100 minus 50, 150. That would be how much? 1 over 3, 1/3. Okay, that means 1/3 of the signal will get reflected. How much is the initial voltage? The initial voltage that is generated here is half of the generator voltage. Okay, half of the generator voltage goes there, then 1/3 is reflected back. Let me show you how that looks like. That's it. And here you see that the signal, when it's reflected back, it also have a reflection, feels a reflection here. And here, luckily, the reflection is 0. So this, how to say, event ends in 2 TPDs. 1 TPD to get to the other side and 1 TPD to get back. TPD is a propagation delay time. 1 TPD there and the other back. Okay, let's go further. The next case, we have Z load less than Z0, and here are the same. So we have the gamma A equal 0, and gamma B would be, sorry, it's F. Gamma B would be 10 minus 50 over 60, which would be minus 40 over 60 minus 2/3. Now we have a negative reflection coefficient. So the positive wave would go there, and then it will reflect back with a negative polarity. You see that? We have a negative wave coming back, and then everything is over. Okay, all that signal propagation with the positive and negative reflectivity or reflection coefficient needs a little bit of extra explanation, I suppose. Because how does that work? The easiest way to show it is actually to try to mimic the signal propagation with this LC circuit. So we have a pulse that generates here, and let's say this is just you're turning on the voltage. So we have a 0 and we have logic 1, and then we keep it. Okay, so what happens then? Then you're building a voltage here, and here the voltage is 0. Therefore the current starts to flow through this coil, and you know the coil has a continuous current, right? So the current is rising through this coil, and then the voltage builds up on the capacitor also rises, and then this voltage, and this one is 0, starts to run current through here, and then the voltage builds here, and then so on and so on. You got the idea, right? So when it comes to the end, the voltage starts to build up here. But what if there is no resistor there? If there is no load here, then the current starts to, this current through this coil, when it rises, then it starts to drop down, and the voltage builds up over the voltage on that capacitor here. So the current starts to flow back, starts to be negative, and then starts to flow back and starts to charge that capacitor with discharged before that. So it starts to flow back, and then it flows back, charges back, and so on and so on. So we have a full reflection, gamma equals 1. If I put a short circuit here, what happens then? When the current comes to here, there is no voltage here. The voltage is 0, right? So the voltage is 0. The current flows through this short circuit and flows in the other direction. And what happens here? It charges this capacitor in the opposite direction and flows further. It charges capacitor in the opposite direction, and therefore it flows back with the negative polarity. So our gamma is -1. If I put now the resistor, which actually has the same resistance as the characteristic impedance of the transmission line, then this current is just exactly that one, like that one, and the voltage is here is exactly equal. So the ratio between this voltage and that current is the same here, which means that the same current flows here and no current gets back, and all the energy is dissipated to that resistor. You can see all that on that video up down here, but I will not show it right now. You can look it up by yourself, and you will see how this magnetic field builds up in these coils and how electric field builds up in the capacitors, and how that happens when you have a short or open circuit or anything in between. So in order to be able to construct the signal on the transmission line, you have to follow these waves propagating back and forth on the transmission lines. And you should first of all know what is the initial voltage. You should know what is the reflection on the generator side, reflection on the load side, and you should now follow the signals which are bouncing back and forth, because it's not necessary that if both reflection coefficients are different than 0, then you would get an infinite bouncing back and forth until everything diminishes into 0. Okay, so let me show you this diagram, which is called lattice diagram. What is that? It's a diagram that helps you construct the signal on transmission line. So what we have here? We have 2 points of transmission line. This is the point A and this is the point B. You know, the beginning and the end. Here we have the generator, here we have the load. Right? And now the thing is, we want to construct the signal. So what we have here? We have the physical dimensions and we have the time. So we have time-space diagram in that sense. Okay, what we do? We have time here, 0. We start here. We put initial voltage on that line, and that voltage then travels along the time here and space. So that's why it's a straight line. And in 1 TPD, in 1 propagation delay time, it hits the load, and it reflects by the load reflection coefficient, and comes in 2 TPDs back to the source, and here it has a source reflection coefficient, so it bounces back, and this wave, you see, it just builds up, it doesn't build up, it gets multiplied with the coefficients, but luckily the coefficients are less than 1 in absolute. So that means that the waves are getting smaller and smaller, and then bouncing back and forth, and also they are losing amplitude because of the dissipation on the track, on the line itself, because of the resistances which we neglected before. And that's why this quite quickly gets into stationary state. So how can we help building up the signal waveform out of this lattice diagram? Well, we can say, let's say we want to know what is the voltage on the point C, which is, let's say, in the middle of the transmission line. This is the easiest way. At the point C, in the middle of transmission line, we'll draw a signal somewhere here. We'll draw a signal T, voltage on the point C, and we will go up to 5 TPDs. So 1, 2, 3, 4, 5. 5 time in TPDs. So let's start. Initially, what you should know, or there is only one rule you should remember, and that rule is really, really important. So I will actually draw it here. The voltage of the signal voltage on a certain position. So signal voltage, okay, let's put it. Signal voltage on a certain position x in time t on that transmission line is a sum of all waves entering x and t from time 0. That's very important to remember, and you should really follow it from letter to letter. Let me now show it to you. Okay. So what do we have here? C. What is the voltage on the line at time 0? It is 0. And this stays the same up to this point. So this point is half of the TPD. So here, maybe I should change the pointer options. In color I would choose maybe green. Yeah, that's better. So until half of the TPD. And what happens at half of the TPD? The initial voltage happens. Let's say the initial voltage is here. So 0, and at half of the TPD I get initial voltage. How long it stays the same? Until here. Here it's the half, 1.5 of the TPD, so here, until here the voltage is the same. Then we get initial voltage times gamma B. Let's say gamma B is more than 0. Let's say it's positive. Let's say it's something like that. So this is gamma B times UE. It's smaller because it's less than 1. So how long does it stay the same? Until 2.5 TPDs. 2.5 is here, so it stays the same. Let's say that the gamma A is negative. So gamma B times gamma A is less than 0, but gamma E is of course not minus 1. Let's say it's more than minus 1, so less, between 0 and minus 1. So it will go down a little bit, but not that much, because it's gamma A is also absolutely less than 1, right? So until here, what we have is this value here. Until at 3.5 TPDs, I get UY gamma B squared and gamma A, and this is a negative value again, but smaller than before because the gamma B is less than 1. So very good, very little, and then continuing to 4.5. Here when I got gamma A squared and gamma B squared, which already together form a positive value. Very, very small. And so on and so on. And finally we get a constant value. So what we got at the end is some final voltage, which we have to check out how much is that. And I followed very simple rule, and that is the sum of all waves entering that position until a certain time is the voltage at that time. Okay. What about steady state voltage? Steady state voltage, that's interesting. The thing is that after this voltage after the waves on the transmission line sort of diminishes, they reach a steady state value, we have to sort of, well, calculate how much is that. So, for example, let's do not now take the generator which has very short pulse, which would mean at the end, of course, the voltage would be zero again. Let's just take the generator which actually changes the voltage between logic 0 and logic 1, and then we have a stable logic 1. So just a unit step source. Now what do we have here now? We have a transmission line, the voltage, this wave. The wave we are interested about is just the transition between 0 and 1. And that wave starts here. We have smaller amplitude, the initial voltage. It goes there. Sorry, I will try to do that like that. Okay, we have initial voltage. It travels there. It reflects part according to the gamma B value. Reflects back. We have gamma A. Reflects back, smaller and smaller, and then and so on, and then it finishes with the steady state voltage. How much is that steady state voltage? That's the question now. At the end, when you have the DC conditions, the transmission line is no longer there. There is nothing, just two wires. And how do we account two wires in our equation? Well, we don't. We just take the final circuit, which actually is just this one here. What's that? It's a voltage divider. So we have a simple normal voltage divider. At the end, the transmission line is no longer there because we have DC conditions. The final voltage, after everything bounces back and forth, is just DC voltage, and determined by the generator and the load impedance and nothing else. Actually, the resistive part, the real part of that. And that's it. So let me show you a few examples now, since we all know how the signal propagates. We know how the initial voltage builds up. We know how it bounces from the source and the load side. And at the end, we know what is the steady state voltage. So that's the first case. Okay, what do we have here? We have a unit step source here. We have the generator impedance. We have it matched, which is equal to the characteristic impedance of the line. Then we have the load impedance, which is less than characteristic impedance. So our generator, or our gamma B, is less than 0. Actually, we can calculate it. We have 10 ohms, we have 50 ohms, we have 50 ohms. So gamma B would be minus 2/3, as you know from before. So gamma B is, okay, minus 2/3, which is less than 0. Okay. So let me show what happens. We can calculate some things more. The initial voltage is half of the generator voltage. If the generator voltage is 5 volts, that would be maybe 2.5 volts then, right? Okay, let's start. What happens? That's the stationary state now. So what means is that we have half of the generator voltage traveling there, UG half. Then it reflects how much back? What reflects back is the minus 2/3 of the half of the generator voltage. So 1/3 of the generator voltage goes back now. And here it completely finishes. So nothing goes back. That's it. Finish. Fair. Nothing else happens. So what is the final build voltage? U final. Well, it's half of the generator voltage minus 1/3 of the generator voltage, which is actually 1/6 of the, half and third, it's 1/6 of the generator voltage. Final voltage is 1/6 of the generator voltage. So I can actually calculate. Okay, 1/2 minus 1/3 is 3 minus 1. Okay, 2. 3 minus 2 is 1/6 of the generator voltage. Okay, so how can I get this value differently? Because now I use this rule of up there, signal voltage, sum of all waves entering, and so on and so on. Okay, I can also calculate the final voltage just by using voltage divider. 50 and 10. So we have 10 ohms, 50 plus 10 is 1/6 of the generator voltage. Seems okay? Okay, what about next? Oh, maybe before we go to the next slide, here are the links, and these links actually are showing the same simulations, and these are very useful. So please check it out. If you don't understand that, try to think about it and then try to reconstruct the signal. Okay, we have a unit step. We have the generator impedance equal to the characteristic impedance. We have the load impedance larger than the characteristic impedance, which means that gamma B would be 100 minus 50 over 150 is 1/3, and gamma A is 0. So what is the initial voltage? Since these two are the same, the initial voltage is 1/2 of the generator voltage. And let me see what happens. Okay, this is it. So you see at the generator side, we start with the half of the generator voltage. Then after 2 TPDs, this is 2 TPDs, we get additional, how much? 1/3 of that generator voltage, and that's it. So the final voltage on that transmission line is 1/2 plus 1/3 of the generator voltage, which is together 6, 3 plus 2, 5/6 of the generator voltage. Okay? What else? Is that correct? Let me think about it. No, it's not. Why not? It's a common mistake also students do. 1/2 of the generator voltage goes there, but 1/3 of that 1/2 is then reflected back. So please forgive me this error here. 1/2 of the 1/3 is reflected back. So we have 4/6, sorry, like that. So we have 1/2 plus 1/6 is 3 plus 1 is 2/3 of the generator voltage at the final stage. You see now here in the middle point, you have half of the TPD to the first wave and then 1 point half, half and 1 point half to the final voltage. But what at the end? That's interesting. You don't see any intermediate level. You see just the final level after 1 TPD. Why? Well, think about it. Think about this point up there. Signal voltage is a sum of all waves entering X and T from the time 0. But you see there are 2 entering this point. One is initial voltage and the other is reflected, 1/3 of the initial voltage. And they do come and are reflected at the same time. Therefore, this voltage here is equal to sum of both at the same time. And this is this value here. Okay. Let's go further. Now the load impedance is less than Z0. The same story before. You already seen that, right? But I will just show it again, just to see how it behaves. See? Now we have the gamma B less than 0. Actually, it is equal to -2/3, if you remember correctly. We have gamma A equal to 0. And we have a negative wave reflected back, which is 2/3 of the half of the voltage of generator, this one here. And the final voltage, check it out. How much is it? We calculated before 1/6 of the generator voltage. And here we did not use this equation to calculate the final voltage, did we? It's just the generator divided by the sum of both, without any knowledge of the transmission line. 150, as you see, is 2/3 of the generator voltage. Okay, so it holds well. This is the case which you already checked out. Okay. Here, yeah. So we have a negative wave reflecting back, and finally we have the final voltage of 1/6 of the initial of the generator voltage. And you see there is some transition going on due to the reflections on the transmission line. But now the things will start to be more interesting. Now we have negative reflection coefficient here, 10 ohms and 50 ohms is -2/3 at the generator side, and also -2/3 at the load side. See, on the both sides we have negative reflection coefficient. And what is the initial voltage? 10 ohms, 50 ohms would be 50 over 10 plus 50. It is 5/6 of the generator voltage. Okay, this voltage then travels along the track. See, now we have reflections back and forth. Stop. Oh, come on, again. That one is not correct. That one is. Stop. So what you see here is we have negative reflections on both sides. The initial voltage is quite large. So the voltage, initial voltage 5/6 is traveling along the track. We have -2/3 of that 1/6 reflected back. That's this one here. Then here minus times minus is positive, goes there. Minus times plus is minus, and minus going back, minus times minus is plus. And there you see the bouncing back and forth. Positive, negative, positive, negative, positive, negative. And summing up, what you see here is that voltage on the generator side is dropping, and the voltage of the load side is rising towards the mid value, which is which one? What is the final value of the signal? The final generator value would be generator voltage divided by half. Why? 10 ohms, 10 ohms. That's the final voltage. But how we get there? On the generator side, we get from the top side to this value, and on the load side, we get from bottom up to this value. And somewhere in the middle, we have the bouncing of these signals. Well, that's strange. And what are these bouncing? And what are they do? What do they do actually? These are sources of high electromagnetic noise that this transmission line can generate and radiate into the surroundings. And this is what we should avoid. But this is a very special case. We usually don't have such cases in PCBs. What we do have is something like that. Well, what do we have here? We have source impedance which is less than Z0. So gamma on the generator side is less than 0. And on the load side we have positive reflection coefficient because the load impedance is larger than the Z0. And this is what we usually have in our digital systems. So initial voltage is quite large, 1050. So you know it's 5/6 of the generator voltage, which is what we want in digital systems. We want the initial voltage is large enough to represent logic 1. And now this one is traveling along. Okay, let me stop now. Oh God, again. Doesn't hurt if I show it twice, does it? So what you see here is sort of bouncing again. Okay, so what do we have? We have almost quite large initial voltage. That's that one here that travels along the line. That one here is in the middle, and this is at the end. And what do we get at the end? Well, reflection at the end, gamma B, is 100 minus 50 over 150 is 1/3. And the reflection gamma A is minus 10, 50, 40 is minus 2/3. Okay, 1/3 is reflected back. This is this one here. See? And then minus 2/3 are here, going back, negative. And minus 2/3 times 1/3 here is minus 2/9. This is this part here. And then this minus 2/9 coming back are reflected here with minus 2/3 again. And this is minus times minus is positive here. And small positive there. And then we get to the final value, which is 100 divided by 10 over 100. So 100 divided by 10 plus 100 is 100 divided by 110, which is 10/11th of the generator voltage. So that's almost close to the logic 1. But you see there are some reflections seen on the signal. So the shape of the signal, which should be on the load side like that, is actually a little bit up and down. So this is the signal integrity problem, reshaping of the signal because of the bouncing of the waves back and forth on the transmission line. Okay, this is another example which is a little bit more to the limits. So we have very good generator. We have large load impedance. So we have the gamma A almost minus 1 and gamma B almost 1. This is ideally, This is ideal system, Isn't it? I mean, come on. We have great generator. We have high load impedance, which means low power consumption. But let me show you what happens. This is what happens. Now I speeded up a little bit this simulation so that you can actually see it till the end. You see that? That's the generator voltage. What is the initial voltage? Is almost, I would say, it's almost equal to generator voltage. So the generator voltage is traveling there. It reflects back almost totally and goes back and reflects that with a minus generator voltage almost totally, and so on and so on and so on. You see how many reflections? The final voltage is equal to 1 over 1k is 1k over 1.001k. That is equal to generator voltage almost. So that means that finally you get the generator voltage, which is good, which is what we want. And the signal at the source size, you see, it's very, very good. But in the middle of the line, we have a lot of ringing at the end as well. And this is the maximum voltage, which reaches almost 2 times the generator voltage, and here as well. Why? Because the generator voltage comes there and reflects back almost the same, so we have twice the generator voltage here at this point. But then, because these values are still less than 1 in absolute sense, we actually have less and less reflections until we reach the final value. So you see that this ringing here can cause quite a lot of problems. The problem is that all that ringing will, of course, first radiate electromagnetic noise, and then second, it would reach voltage levels above the power supply voltages, which can cause some noise transferring into the integrated circuits which are then connected to them. And they could maybe, I don't know, I haven't seen that in real life, but it could also damage the inputs in these integrated circuits. So all that should be avoided. This is really, really a problem. So we are sort of distinguishes 2 line driving modes. The first is underdriven and the other is overdriven transmission line. Underdriven transmission line is when we have positive reflection coefficients on both sides. So high resistance sources and high resistant loads. So the voltage is then building up to reach the final value, and it's approaching from the bottom side. Here, the overdriven line, when the I would say or and or one or another is negative, we have ringing. Because if one or another or even both reflections are negative, then you would get positive and negative waves traveling back and forth, and this will always give you some sort of ringing. And this ringing is, of course, not wanted. This is a bad thing. So please, ringing is never good in such cases. This one actually would, in case of slow signals, even make it better in the sense that the transitions, the rise times are then consequently lower. But lower rise times would then mean less radiation. But that would again, on the other hand, mean that you cannot transmit fast signals for these transmission lines anyway. But nevertheless, you can afford to have high resistances of your sources, and as long as you keep your load at very high resistances, that would finally reach the logic level you need, but it would take some time. If you have low resistance sources, you finally reach logic level reach immediately, but then you have ringing. So all that is a problem. And typically in transmission lines in digital CMOS circuits are always overdriven. So these transmission lines, because of the loads which have high impedance, inputs, and sources which are very good, would give you overdriven transmission lines. So the question is, where should you care? When or where should you care about that? What is the criterion that will tell you, okay, I want to care about this line because it's very, very critical, but I would just leave the others as they are. I wouldn't care about it. So what's the criterion to choose which track, which line, which connection on your PCB is critical in that sense? Well, critical transmission line length is determined by this very, very simple criterion, which would tell you the rise time of the signal with respect to the 2 times propagation delay. Why is it that? Well, the time needed for the signal to come there and reach back is time 2 TPDs. Now, if in this time, when the signal goes there and returns back from the load back to the source, your signal is just reaching the logic level, this would mean that your signal is slow enough for this transmission line not to affect it anymore. Look at here. If we have very slow signal, it means that the rise time is, let's say, equal to 8 TPDs, you would have this option, this case. See? No ringing. But if your signal is very fast, like this one here, you would see the green, a lot of ringing. So, what is the criterion? That one here. This is the limit value. The rise time equal to 2 TPDs. The rise time means that just when your signal reaches top level, the return signal came to your source. So you get a triangular shape of the waveform. And this is the limit value. And you may also see that it's better to be far from that. So let's say the optimal would be 4 TPDs, because there you have this blue, light blue curve here. Still ringing, but not that much. So this is the limit value, this is the criterion, you should be here. And the TPD is determined by the speed and the length, because you know that the speed is length over TPD, and this is the critical length then. If you know the speed, you can calculate the critical length is equal to speed of the signal over the the critical length, is that correct? Yeah, surely it's correct. The L critical is then equal to speed times the TPD, and the TPD is actually should be in the range of T rise half, and that's important. Now the rise time determines the critical line length, and if the rise time goes lower, the critical line length also is shorter, and if the speeds of the signal are slower, then the critical line also gets shorter, and that's important to know. The next question, how does the capacitive loads on the transmission line affect their properties? Because we know that there are some, at least the inputs of the digital interfaces, the inputs to these are have some small capacitance, and this capacitance can be added to the transmission line capacitance. That's one thing, and the other is we can add a capacitor to a transmission line, just for fun or any other reason. Actually, we could do that. So how does that affect the transmission line? Well, if we add the transmission line to the transmission line additional capacitance, let's say that the load has some capacitance, or we add it by ourselves, then we can say, okay, this capacitance influences the transmission line as if it was distributed along it. At least to a certain extent this is true. Not totally, of course. So we can say, okay, the characteristic impedance of the transmission line is this one here, and we say, okay, the total inductance, total capacitance, we add this load capacitance to it, and then we can divide by the unit length. Let's say we say I want our inductance to be in nanohenries per centimeter, capacitance in picofarads per centimeter, and so on. So we say, okay, the load impedance is distributed by the length in centimeters, and this can be put in as a distributed per 1 unit length. And then the speed of the signal is also calculated correspondingly. So all that can be then included and recalculated. So what happens? As you see that the load capacitance actually decreases the characteristic impedance of the line, and it also decreases the speed, the propagation speed. So if we add the capacitance, we are decreasing propagation speed. That means that our track, our transmission line, if it has decreased speed, it will prolong the propagation delay time. If the propagation delay time is prolonged, then the critical line gets shorter. You see here? The critical line gets shorter if the propagation delay increases. Because if that one increases, then the rise time of the same line would also have to increase. And that's the reason, okay, if the delay is longer, it's like the line itself, it's longer. So the longer line has the same time, or let's say the line feels like it is longer, which means that the critical line length gets shorter. Now, effect of additional RC filter is also present because there is a resistor here usually at the input. So we have some sort of resistance of the generator, and that one then increases the rise times because the adding additional capacitance would increase the rise times. So that means that if the rise times are increasing, then the critical line gets longer. So what is then prevailing? If you have really good low source resistance sources in your design, then the decreased speed is prevailing. So you have to, if you add capacitors, you also have to add a certain resistor. And by this RC filter, you are actually prolonging the rise times and therefore making your transmission line less critical. So adding resistors together with capacitors would be one of the ways of making your transmission lines of the certain length less critical. I did some simulations of the capacitive loads on this transmission line, and I changed the capacitance of these loads here from 1 pico to 1 nanohenry, and what you see is 1 picohenry is here, the green one, then 10 pico is the blue one, the red one is 100 pico, and when I really increase this capacitance to 1 nano, I would actually decrease the rise time so much that it doesn't have any effect, significantly have any effect of the rise here. The problem is that 1 nanofarad is quite a lot to put on your transmission line. And of course, because of that, you also see that now these rise times are so slow, you cannot transfer fast signals anymore. So this is only a solution if you have a slow signal with very fast rise times, which are not needed in that case. Then you can slow them down by adding a capacitor, but much better also adding a resistor. So how to calculate transmission line lengths, critical transmission line lengths is shown here. What do we have? The speed of the signal is determined by that equation. This is the characteristic impedance. Then we say, okay, our transmission line typically has around 3 nanohenries per centimeter inductance. Okay, this can be, this is a rule of thumb, let's say value. We say that the load capacitance CL is around 15 picofarads. This is the capacitance of the chip, input capacitance of the chip. And then we can compare the rise times of these logic families which we have. We have the rise times and the fall times, and they could be equal or different. So anyone, rise or fall, we take the smallest one. So we take the smallest value among those two as a rise time, and we compare it to two TPDs. How do we calculate TPDs? Well, we have to calculate the speed. How do we calculate the speed? Well, we have to know the L and C value. The L is this one here. The C value can be calculated out of the Z0, and the Z0 is shown here. So these are different characteristic impedances of the lines, and then you can calculate the speed, and out of the speed you can calculate the TPDs, and then calculate the critical line length as a speed times rise time halved. And these are the values here. As you can see, the critical line lengths are getting longer if you have larger impedance of these lines. So having large impedances would give them more free space for the lengths. So that means that you don't have to care if you have 2 3 centimeter length of your track if the impedance of that track is high. But for certain standard communication lines, this impedances are well fixed. So I'm talking about 100 ohms, 90 ohms, or 50 ohms. These are 3 different very standardized impedances. So for 50 ohm impedances, you see that these critical line lengths are getting down to a few centimeters. But these are critical line lengths. You know that you should be on the safe side. So maybe checking this here, we should be at least here, which means that we have to go not to the limit. Maybe we should go just to half of this length. So if we don't want to care about the reflections of the signal on the transmission line, it should be half of this value. So we're talking about maybe 2 centimeters here, 4 centimeters there, 5 centimeters, 6 centimeters here. If the track is longer than that, then we have to care about these properties and we have to deal with it and correct it. This can be all done by different techniques, which are all summed up in one single term, which is called transmission line termination. So from now on, we will talk about that, and this should be done in the next part of this lecture.